So hello all, pleasure to be here. I should thank the Center for Arctic Repair for hosting us all on this beautiful facility and on this lovely day. So Pete talked a bit about the science behind SAI. I'm going to focus more on how we would do it, logistics and reasons and constraints that the logistics place on what we could do. As Pete earlier discussed, in order for SAI to be effective, and by the way, I'm going to talk only about SAI and not about MCB in this talk, but in order for SAI to be effective, we need to put the material above the troposphere, above the tropopause boundary between the troposphere and the stratosphere, and well into the stratosphere in order for it to be effective. If we place it in the troposphere, it comes down in on the order of a week. If we get it into the stratosphere, it endures on the order of a year, and so we get vastly more reflective forcing if we get the gunk up into the stratosphere, as only the very largest of volcanoes do, but volcanoes occasionally do this, and that's the analog that demonstrates to us the high likelihood that this would in fact work. But the tropopause altitude is not constant across latitudes. It is high in the tropics and much lower near the poles. It is 16 or 17 kilometers in the tropics and about half of that at the poles. I've put two stars here at 15 north and 15 south. Those are two of the commonly considered deployment latitudes where we might inject such material. And you'll see that we're at the peak of the tropopause altitude if we're there. We don't want to deploy right at the tropopause. We want a margin to ensure that we're well into the stratosphere to account for variability of the stratosphere altitude. And so the commonly discussed altitude for deployment in the tropics would be 20 kilometers both north and south of the equator. But to the extent that we deploy into the stratosphere, we then expect the Brewer-Dobson circulation to take the precursors and or aerosols that we would deploy from the equator to the poles and thereby envelop the entire planet in a protective veil. The problem is that very few aircraft get as high as 20 kilometers, and those that do carry approximately nothing. Many of them leave their pilot on the ground, they carry so little. And so we would need new aircraft in order to be able to undertake the mission that I just described, deploying millions of tons of material a year at 20 kilometers or more. But it's not that we can't design such an aircraft. It's just no customer has ever needed a high leaping dump truck. But if we needed one, we could design one. And with a team of former Boeing engineers, we did create a preliminary design for such an aircraft years ago. This is the Stratospheric Aerosol Injection Lofter, or SAIL-01. And you'll see it has huge wings with lots of wing area to generate lift at that high altitude. It has 6 engines rather than the now customary 2, all to haul a skinny, pencil-thin little fuselage up to a high perch where it could then dispense its chemical load. But this plane is designed with existing engines, existing avionics, existing wing planforms, existing materials, all to demonstrate that there's no unobtainium needed to develop an aircraft that could do this mission. So this could, if we needed to do this, we could do this. A problem, however, is that developing a novel aircraft, as that would take roughly a decade. I've laid out the developmental spans here for a variety of modern passenger day aircraft, and you'll see that they take on the order of a decade to develop and certify and test and get ready for entry into service. And that decade got us one airplane. In order to do a substantial intervention into the climate system, we will need hundreds of aircraft, and that will take roughly another decade to build out. So one should imagine that if you had a goal to cool the planet by half a degree or 1 degree, it might take on the order of a couple of decades from the time you push the button for a funded launch to the time that you've achieved your temperature target. You can start in year 10, roughly, with a few aircraft, and this is something we wouldn't turn on in a binary fashion like a light switch. We would start small and ramp up, but still, this isn't something that we should conceive as an emergency response to a climate surprise. This is something that we should, if we intend to do, plan to do and give ourselves time to ramp into. But if we developed that fleet of high-flying, heavy payload aircraft, we could then deploy. This illustrates the commonly discussed 30 north, 15 north, 15 south, 30 south base array that one might consider. And so I've illustrated that array on 4 continents here. This is roughly the north-south span of Africa. Cairo is at roughly 30 north. Durban, South Africa is at roughly 30 south. And so that's the north-south band that we might consider if our goal is a global veil that is roughly homogeneous across the planet. But I'm going to suggest that there's a better plan than a global veil that is roughly homogeneous across the planet, at least as a way to start. And that better plan would be to put parasols over the poles. Not the poles precisely, the subpolar regions, but I'll hereafter call it the poles. But the reasons that a polar-focused early deployment program might be better are, firstly, if we think the climate is broken, the place to start that repair is the place that is most broken, and that's the poles. The Arctic is heating at roughly 4 times the rate of the planet on average. The Antarctic a little less, but Arctic or polar amplification is a very real phenomenon. So these are the ecosystems that are most urgently at risk, and if we've invented some new ointment by which we can help repair the climate, a sensible target for that deployment would be the places that are heating the fastest. These are remote targets, at least for most of us, but I'm going to return to the unique perspective of northern peoples in particular a little later. But these are targets that are remote from the rest of the world, and yet I don't want to suggest that these would be, interventions in the poles would be contained to the poles. The permafrost, and neither are the impacts of polar amplification, by the way. The permafrost that is melting in the poles would heat the entire globe. Similarly, ice that is melting at the poles would raise sea level generally. Stabilizing the AMOC and the other polar tipping points that Pete referred to would have global impact as well. This would also be a considerably smaller program in terms of deployed mass. If we're trying to put a veil over the entire planet, we would require many times the deployed mass that would be required if we're trying to put parasols over the poles. And to the extent that there may be unintended consequences that would derive from such a program, and there still may be, having a smaller intervention by which we start would thereby reduce those risks. So if we were undertaking this polar deployment scheme, we might seek to deploy in the north from Anchorage and Stockholm, where I've put these stars here, both of which are at roughly 60 north. And again, the Brewer-Dobson circulation would still operate, so our material would continue to flow poleward from there. So deploying from Anchorage and Stockholm, for instance, would put a veil over the North Pole. In the south, there is no landmass at 60 south. The best we can do is about 54 south, the tip of Patagonia, so Chile, Argentina, the Falkland Islands are not far from there, but far fewer deployment base host opportunities in the south. But nonetheless, this latitude would work as well. And so if I go back to my tropopause chart, we've got my stars here are now at 60 north and south. I'm going to gloss over the fact that we earlier discussed we probably have to deploy at 54. But if I put my stars at 60 north and south, you see I'm way down on the tropopause altitude chart. If I give myself the same, these stars are roughly 10 kilometers in altitude. If I give myself my 3-kilometer margin to ensure I'm well into the stratosphere, I'm deploying here then at roughly 13 kilometers of altitude. That's important because existing wide-body aircraft can get there. The service ceiling of the 777 is 13 kilometers. Same for the 747 and the 787. The Airbus wide bodies top out a little bit lower than that. But the point is we could get there with existing aircraft. That's not a reason to do it there. I'm not trying to sell it in that way. If this is a good idea, it's a good idea for other reasons. But the ramp up to do it would be much easier and cheaper and faster because we can use existing aircraft. We don't need that 10-year span to develop a new aircraft. Now, we can't, of course, use a passenger 777 in exactly its current configuration. We would need to tankerize the aircraft, take out all of the passenger service seats, galleys, lavs, and install the aerosol tanks and control systems and nozzles that would be required to make that airframe operate as a tanker. But the point is we could deploy at the poles with existing aircraft. We wouldn't, the focus of this conference is the Arctic, and I keep saying polar, because to the extent that we wanted to do this at the North Pole, we ought as well to do it roughly symmetrically at the South Pole in order to not goof up the ITCZ, the Intertropical Convergence Zone, that is sort of the climactic equator. The ITCZ informs the monsoons on which so much of the tropical world relies, and so we wouldn't want to deploy only in the north. We would seek to deploy, as I say, symmetrically, but you could do so with the same fleet because you would only deploy in the local spring and summer. So for instance, if we're deploying in the north, we would deploy in March, April, May, June. That gets the material into the summer sky. By fall, it begins to fall out, but the light is disappearing then, so that actually works well. That same fleet would depart Anchorage and Stockholm if those are our bases, but Helsinki and St. Petersburg and other places would do. Go to Dallas or whatever for maintenance, fly to Patagonia to deploy in its local spring and summer, September through December. So a single fleet ferrying between the poles could cool both poles. This, I've already regretted putting this in because it's hard to make sense of, but the punchline is this is a figure from a paper that Ali and Pete and a couple of other authors did on the impacts of polar solar geo. The top purple lines is the one to focus on. The punchline is if we're deploying where the circles are at 60 north and 60 south, most of the material, which are the cubes, flows poleward as we would expect per the Brewer-Dobson circulation. But oddly, the centroid for the radiative forcing is equatorward of our deployment points at roughly 50 north and south. Well, if most of the gunk went poleward, how can the radiative forcing be greater equatorward of our deployment points? It is because the stuff that flows equatorward has a much longer atmospheric lifetime, and it encounters much more direct sunlight. So the minority of the material, in fact, does the majority of the reflecting. So we have substantial direct impact equatorward of our deployments, even though they're done at the poles, and indirect impact even farther south, because cooler temperatures will draw heat from the tropics. So this should be considered a global intervention. Whether the governance of a polar program would be easier than that of a global program is unknown at this point, and a topic to be discussed and considered hereafter. And whether it would be more acceptable to public opinion is also unclear. This may be seen by peoples in the Arctic, for instance, as a helpful fire extinguisher to tamp down polar amplification, and it might equally be seen as an unwelcome bit of climate colonialism, and so that too would need to be explored. But if it succeeds at the poles, we could then begin to move deployment back equatorward, so that we may end up with the global veil that we initially discussed, but by getting there via a deployment at the poles. Questions?
Time.
Hi, I'm Claudia Wieners from Utrecht. I have a technical question about these stratospheric planes. So suppose that we would not get an airport where we really wanted. How far could they move in the latitudinal direction, like without making the design totally messy because of whatever, the weight for fuel or that kind of stuff?
So of course, planes fly, and they go from, New York to Singapore, so they must be able to go a little bit north or south. The problem is that the planes take off with their max payload and max takeoff weight, which consists of payload and fuel. To the extent that we've got a long commute to our deployment location, that will reduce the amount of payload that that flight can carry. Now, if there's something very important about that airport and that location, you could commute. But in the ideal way to design such a program, you would fly up, pop your cork, come back down and get another load, and not commute long distances, because that will require less payload and therefore more airplanes to deploy the same lofted mass.
So suppose you would have to commute 1,000 kilometers, how much % of your payload would you lose, very roughly?
Enough that you wouldn't do that. You would choose airports. There's no longitudinal reason why we need to be at one place versus another, and therefore you would likely deploy pretty much directly over your airport. I wanted to see that. Thank you.
You're welcome. Basically, a more specific follow-up on the same sort of question. Building a large new airport on Tierra del Fuego would be pretty tough. So can you comment on Cape Town, Melbourne, 40 degrees south?
They're way farther north than you think. So Tassie or the southern island of New Zealand or Cape Town are all way less good than Chile, Argentina, Falklands. But because of this very issue, I have commenced a program with Chile and Argentina to look at the time requirement that would be needed to build out either Ushuaia and Punta Arenas to expand those airports to carry this sort of capacity, or to build new airports nearby. So in a year, I hope we'll have a paper out on what those countries told us would be the time span needed to accommodate this kind of traffic.
Hi, Alex Lupke, Ice Preservation. 2 questions. Number 1, lighter than air platforms. Have you considered that? And is there any kind of design around that?
Yeah, they don't carry jack.
Well, anyway, I come from Google X. I help run the Loon program. We basically had thousands of stratospheric flight platforms. Our payloads were 100 kilograms. But there's a concept there. We spent over $1 billion in order to develop these programs, right?
My very first paper in this arena was on alternative platforms, and most of the other platforms other than fixed-wing, self-propelled, air-breathing, subsonic aircraft are about 10 times the cost per lofted ton, and balloons or lighter than air platforms are that way as well. They're also slow to ascend and descend. So
we should talk. There's some data out there.
Let's do.
Second question, you sort of said just pop your load. Like, would you want to distribute the material? Like, if you just put it up there, does it actually distribute evenly?
Depends on the material. So another thing that this community is focused on is if it's sulfur, what form of sulfur? Is it H2SO4, in which case you want to ladle it out spoonful by spoonful over a long cruise because you're concerned about coagulation? Or is it a slow oxidizing gas like SO2 or H2S, where you can dump it all out like a World War II bomber because it will disperse over time. Now, even that latter analogy is wrong. So how long a cruise is required is an open question that this community is trying to work on. And the material may not be sulfur either. There are solid aerosols that are considered as well. So I'm using here the simplest example, which is something where we think we could just open the valves, but it may not be that way.
One quick last question here.
Thank you for interesting presentation. You said that the thing you put in the stratosphere will last for at least long time, years, not months or weeks.
That's true if we put it near the equator. The atmospheric lifetime would be about half that if we put it at the poles, as I discussed. So I skipped over that detail, but still we get much more atmospheric lifetime by being in the stratosphere.
So in the northern Arctic, North Atlantic is warm, and we have the half of the year dark. And that's a very important time of the year to lose heat. Wouldn't your thing then insulate? So we will not lose the same heat. While when you go to Antarctica, it's different. So your argument that you should do the same both places is not necessarily complete, or is it?
I think that it is, with the caveat that all manner of things here we don't know. I'm expressing more confidence than we should about everything here, but insofar as we know, again, you would deploy March, April, May, June in the north. It would sediment out by the fall, such that by December you mostly have no material in the air, and therefore it's not insulating in the dark winter. But I've simplified too much. It doesn't happen quite as mechanistically as that. Doug, did you want to say something before I run off the stage?
Just what you were about to say.
Okay.
Lifetime's like 5 months up there.
Yep. So much shorter lifetime because it's already near the poles, which is where it was going to be taken by the Brewer-Dobson circulation. Thank you for your time.